Well, hello guys, my name is Alexis Ortiz. I'm from Colombia and I made this video in order to present you my final delivery to the course Artificial Life, which took place this semester, the first semester of the 2018. Uh, this course took place in the National University of Colombia. Um, well, let's show you what's in there. So as you can see, I decided to make my project in the Unity 3D editor game engine. So we have some C# codes and some 3D assets which I use in order, free 3D assets which I use it in order to make my work easier. So the goal of this project was to make an evolutionary environment which relied on some individuals, some predators, and these individuals should too take some food, eat some food. So for the individuals, I decided to use a sardine, a pretty nice sardine. For the predators, I decided to use a prehistoric ammonite, and for the food, I choose to give the sardines some banana plants. Alright, so let's see what we got over here. In the scene, you can see I have this nice background of an underwater picture to give some underwater ambience to my sardines and my predators. We got a fish manager which is used to manage the fishes and store them in an array. The predator manager which makes the same for the predators, and a plant manager which only function is to store the food for the sardines. So as we can see, the fish manager got a script which I called global void. The global void script got a prefab, fish prefab, which is this prefab over here. This prefab and the number of fishes will allow us to instantiate all the fishes that are necessary to reproduce our simulation. A predator manager which makes basically the same. In this moment we have no predators, and a plant manager which only uses a prefab to instantiate the plants. We don't have a number because the plants instantiate in runtime. At the beginning there is no food, so that's it. Here we got to see a little of the code for the global void. So we iterate over the number of fishes. We create a random position within a threshold, which I call a tank size, the size of the tank. I can accept that this code relies heavily on some old implementation of other fishes voids, but I had to modify it like a lot to allow my fishes to have reproduction, predation, and they look for food. So we made the fish and we add it to an array which is called fishes. Every 100 iterations of the frames we get to see the status of the void. The status will give us an average of the speed, the minimum and the maximum. Same for the health and same for the vision of the fishes. The predators in the simulation don't evolve, so the predator manager only is to instantiate these predators. As you can see, the script for this predators is called global pack, as predators moves in packs, not in voids. So we only instantiate the predators like the same as the fishes. We let him alone. Now let's analyze the fish itself, the fish prefab. The fish prefab relies on a script which I call it fish component. The fish component got the fish prefab itself in order to allow the fish to reproduce. so a fish can instantiate another fish. We got some upper bound and a lower bound for each dimension in order to allow the fish to move in certain restrictions. We got a fish's speed, a rotation speed, the fish's vision. The vision allows the vision tells the distance in which a fish can see either food or either a predator or either another fishes in order to don't make a collision. But when these fishes still make a collision, we got a reproduction probability, which will tell us how many times these fishes will reproduce. Every time a fish reproduces, we got its genetic code, and its genetic code can have a probability to change and make a mutation. So we got a probability of mutation for each character of this genetic string. We got the fish's health and its scale limit in order to don't allow our fishes to overmutate its size. With our scale limit, the fishes get too large and make a lot of conflict to the simulation. So we had to make scale limits. And it's really nice to know that the speed, the vision, and the health don't necessarily mean that the fishes are going to get these values, but these values are going to be generated in a random way. So we can see it here in the fish component. Every time we instantiate a fish, if it is not predefined, we are going to make the fish with its max health is a range, is a random between a 9/10 of the fish's health and the fish's health. The max speed can be 0 to or any value to the fish's speed, which we set up at the beginning, and the vision is same. We got the modifier for the scale, which I used to make some different size fishes. So when we run the simulation, we're going to see some fat fishes, some large fishes, some tiny fishes, some big fishes. Here we set the health to the max health. The health is going to be downgraded with each iteration of the simulation. Every fish is alive. We got its speed. The speed is not the same as the max speed. The fish can be very quiet but have a very high max speed. So the speed is the initial speed. And we can see we got another variable, so like hidden, is in fact same, almost same as max speed. The metabolism will tell the fish how fast is he going to consume its health. So the faster a fish move, the faster he will consume its resources. So a slow fish will live very long, and a very fast fish will die very rapidly. We can see the ammonite is almost the same, but without reproduction. We got some nice effects for the blood when he eats a fish, and a nice crunch when he eats the fish. Well, we got some parameters. Our predators doesn't have necessarily the same vision as the fishes. We got a vision for its neighbors, and a vision for the love. They love to eat sardines, so it is the love distance which they are going to use to see whether or not they follow a sardine. And we have these plants over here, which uses the Earth system script, which allow us to create some nice Earth systems. I would like to show you the Earth systems we made based on the overall bracketed Earth systems. As you can see, we got these plants. We got a rule. You can see the rule here. The rule over here. We can see another rule. Each plant has its own rule. Um, so if we turn the fish manager and the predator manager to 0, we can see that uh, there is only these plants. This plant relies on uh, what we're going to call a cube, which is like some stick, which I used to make these plants. So let's see. We got these plants, which uses the cube. If we make the cube kinematic, the plant is going to be quiet. It's going to be still. The word is still. So let's see how these plants look. So we can see these plants, and we can see they are generating food. The food is generated over some stations. Seasons is the word. We can see this plant generate the food in relation to the time. They begin to generate food depending on the season they are. If we make these plants, if we make the stick non-kinematic, we're going to see these plants move like some kind of algae. So let's see. Here we can see the movement of the plants. It's very nice. I worked too hard on this. I'm very proud of these plants. So we got to see the plants. I'm going to remove the plants for a while we analyze the fishes. I'm going to show you a simulation with 100 fishes to see how they see and how they move in bites. So that's it. Every time a fish is created, they made a sound and a boom in order to see the creation of the fish itself. So here we can see that our fishes are not all the same size. We can see here a very fat guy. This fish is like a very ugly fish, but we can see that these fishes are very different scales and very different sizes. Every fish which has a bigger size will also have a bigger collider. We can see it over here. We can see this collider of this fish is very large in comparison with, for example, this fish, which have a collider very small. So the smaller is a fish, the fewer probability he will have to reproduce, but he will have less probability of being eaten. Will have less probability to collide with a plant. So these little fishes has lesser probabilities to eat, but have higher chances to survive. So let's see it again. So we got a nice simulation running. Our predators relies on another script. Here we can see it, which is a Turing morph script, which allows our predators to have morphing skins. So let's see it in action. We're going to remove the fishes and instantiate some predators. The predators have a Turing morph skin, which must converge in order to make the simulation faster. So while the skin converge, the simulation will turn out very slowly. But as soon as the skin is converged, the simulation will go very smoothly and nice. So let's see how these skins are looking. So we got 3 ammonites. They are moving very slowly because, as I say, the simulation is converging. We hope to get some nice results for the Turing morph script. So we can see the skin of this ammonite is very spotted. The skin of this ammonite is slightly spotted, not as the first, and the skin of this ammonite is totally red. It converged every cell, every color cell to a true state. Well, so let's see the whole thing in action. We got our predators or individuals on the plants in the same environment. I decided to make this little script over here to show you the values of the population, the evolution of the values of the population with the time. We get to see that we got the minimum speed, the average speed, and the maximum speed of the population of all the fishes. Same for the health and same for the vision. We can see that the speed is not always getting higher, because a better speed is not necessarily a better evolved individual, because the faster is a fish, the higher he will consume its health. So the speed is going to get a little down until it converges to the ideal speed. We can see that the simulation is a little slow, but it's only while the skin of these predators converge. We can see over here that only one object has converged, so we must wait for the Turing morph script for the skins of the predators to converge in order to make a smooth, nice simulation. We can see that I think we got it. All of our predators did converge is skin. So we now can see the evolution of this environment. We can see that the health is getting higher. The vision is varying with the time. The speed is not necessarily getting higher. Speed is like going down, as you remember. Not necessarily we need higher speeds. We can see that we got some highly mutated individuals which ruin the average value, but they die very soon. So the average value of the speed will normalize very soon. We got to see that the value of the health of the population is always getting higher, so we can see that the species are really getting a better health with each iteration of the simulation. The vision is getting higher and higher. It's not necessarily good to have a great vision, because with a large vision the fishes will only escape, so the vision is going to vary like a lot. So that's it. So here we can see the final result of our simulation. We got to see the predators, the evolution. We got to see the fishes, the food, the seasons of the food. I hope you all guys like it. Sorry for my not too good English, but this is what it is. So I hope you liked it. And if you like some answers, or you have some questions, you can always email me. So thank you for everything.